Many of you already are familiar with the NanoFrazor as a high-resolution patterning tool. Right? The way that thermal scanning probe lithography is implemented in our tool allows us to write sub 15, sub 10 nanometer features routinely. We combine this capability with carefully selected thermal resists in order to accommodate the processes further. So our favorite resist actually is the thermally decomposing polymer PPA. PPA locally decomposes when it is heated and turns into volatile molecules that are then removed without much residue. This reaction is endothermic. It does not spread around to neighboring molecules, and therefore we don't see proximity effects that lots of E-beam users are very familiar with. This also means we're not limited in the type of geometries we can write. We are quite free in choosing arbitrarily, be it the standard lines and spaces and corners for benchmarking purposes, all the way to the most creative designs we get mostly recommended by our users. The patterning capability is combined with in situ reading line by line. As you will also get more details if you have already watched or would take the time to learn through the other webinars in this series. There is the built-in topology sensor in the NanoFrazor that allows us to immediately inspect what we have written. And that way we can immediately correct writing parameters if necessary. So today we will talk about this process on the left that is based on a 4-layer resist stack that can take advantage of the high resolution and high feature density patterning capabilities. Now, this process gives us good and tunable etch selectivities. We can work also with many different substrates and many different underlayers. So this very specialized process is actually at the same time quite versatile. There are a few examples that you see already on this slide, but you also will see a couple of applications examples towards the end of the presentation. The NanoFrazor processes are compatible with standard pattern transfer techniques. You see some of the techniques depicted here that will look familiar to many fabrication researchers and workers. In the case of the high resolution etch, we focus on a 2D process that can be applied on a very wide variety of substrates, including of particular interest 2D materials that can be quite sensitive to oxygen or ion bombardment and so on. So this particular process is very suitable for use with sensitive materials. There is one quite significant limitation to how high a resolution we can pattern, and that is that the heated tip that we use for thermal scanning probe lithography is shaped as a cone. You see a TEM of the image on the left on this slide, where the apex itself is under 10 nanometers in diameter. That's wonderful, but it widens quite quickly, getting away from the apex of the tip. So when we look at the cartoon on the right-hand side, you see that the deeper we write with this cone into the resist, the less of a high resolution we will be able to achieve. Say we have an 8 nanometer thick resist and we want to write 5 nanometers into it. We leave a tiny bit of buffer for robust processing later on of about 3 to 5 nanometers, that's fine. Then we can write very, very narrow line spaces. If the same exact procedure is repeated with a 16 nanometer resist of the same exact everything else, then the line that we write will be quite a bit broader. In order to address this, we will go into how we use very, very thin layers of resist and how we can make them happen. The other motivation we have to stay with very thin resists is that the thicker a resist is, the more likely it is to collapse during subsequent patterning. In fact, the likelihood that pattern collapse will occur, just like the nightmarish pictures that you see on the right, is linearly dependent on the height that it must carry, so the thickness of the resist. For that, we go to spin coatable, very thin resists that are made possible by collaborations we have been carrying on with very innovative and very reliable partners. One of those is a spin coatable siloxane polymer that was developed by the Finnish company PyBond for NanoFrazor technology. This resist can be spin coated into a 6 nanometer film. It can then be exposed to a mild oxygen plasma to remove the organic content. And what results is a pinhole-free, very smooth 1.5 nanometer silicon oxide film. In subsequent processing, this film behaves much like evaporated silicon dioxide and can be used in, for example, reactive ion etching steps as a protective layer. On top of the spin-on hard mask, we use, as I mentioned, very thin thermal resists. That is then our standard PPA in thicknesses ranging from 8 to 15 nanometers. 8 to 10 nanometers is a very good thickness to start. But that means the tip that we have, this very sharp tip that is made out of silicon, is in close contact with the hard mask, with the silicon dioxide spin-on layer. In order to make sure we don't get a lot of wear and tear from this surface interaction, we put a buffer layer in between. And that can be an ultra-thin PMMA layer of only 2 nanometers thickness that already takes care of making sure our tip life stays within reason. The PMMA layer also acts as a thermal insulator and improves the patterning performance quite a bit. So I mentioned 4 layers. That's our thermal resist, our buffer layer, and the spin-on silicon oxide. Underneath it, we have a rather free choice of the organic transfer layer, as we like to refer to it. This layer is there for increased selectivity when etching and for helping us make our processes quite a bit robuster than otherwise. For the organic transfer layer, we have also collaborated with PyBond, and we prefer the layer that is based on a fluoranone polymer that is now available under the product name OTL405. Now, this layer can also be spin coated, and its thickness can be varied between 10 and 250 nanometers. So then you can look at your selectivities, you can look at what is underneath and what you want to etch, and you can choose the thickness of the transfer layer that you spin coat. And this allows for quite a large process window for you to play with. One thing to be careful about with this particular underlayer is that the soft bake temperature is well over 200 degrees. So depending on what is underneath it, it may or may not be a showstopper for some processes. And for that, we then go to a wide variety of other organic transfer layers available. So we spin coat this resist stack, then we pattern our desired structures using the NanoFrazor. We then do a very short oxygen-nitrogen plasma descum process. It is only a few seconds to remove this very tiny layer of PPA that we prefer to leave on the substrate in order to make processes more repeatable. After the descum layer step, then we can go on to use CHF3 to etch the silicon oxide layer, and then a mild oxygen plasma to open the organic transfer layer underneath. Once we have done that, we have now reached the substrate. It has now been opened. Then we can continue with, for example, reactive ion etching to continue into the silicon substrate in this case. We can alternatively take ion milling and also process metals. And we can also, if we want to, for example, create very high resolution and high quality contacts to nanowires, or we want to make plasmonic structures, then we can use this process with slight modifications for liftoff. Okay. For liftoff, we recommend using PMMA as the underlayer. And that is because even though the oxygen plasma that we use for opening the organic transfer layer goes straight down, you still, especially if you over etch just a bit, you get a little bit of an undercut, which is enough to then carry out a liftoff process. And so you open the resist stack as I described earlier, and then you carry out the evaporation of your metal, and then you can remove PMMA as you would in any liftoff process. And this we have shown to work for thicknesses up to 60% of the PMMA thickness that you choose. There are a few limitations to the high resolution etch processes that I mentioned before already, that these are for 2D features only. I can imagine that we can, with a bit of creativity, expand these processes to 3-dimensional features. If you're interested, do get in touch with us and we will do that together. The other thing is that these ultra-thin layers are quite sensitive to contamination and must be used carefully. And it is also highly recommended to check the quality of the quality of especially the spin coatable hard mask periodically. In case you start seeing pinholes, like in the topography image here on the left, shown with the red arrows, or your roughness starts going above half a nanometer, then it means there is some contamination affecting the performance of the hard mask. On the right, you see a topography image of a perfectly fine layer. This is what it should look like. This is what it does look like most of the time. I also have mentioned repeatedly that the etch processes that we use are gentle processes. And this is not always the case with any standard RIE machine in a multi-user facility. So it is important to calibrate the etch rates and to make sure that you also take into account the ignition effects of the etch tool that is at your disposal. If the undercut that results from over-etching the underlayer is too large, then your features will also be broadened accordingly. Of course, when we take these limitations into account and we're careful about them, then actually quite impressive applications can be achieved and have been achieved by our users. So here you see this etching process applied to molybdenum disulfide flakes, where the flake itself was etched into a set of ribbons. This was made using reactive ion etching. And then 8 nanometer wide ribbons were created using this process. Also, an increasingly popular application is an array of carefully and repeatably created holes. Okay? So these matrices can be used for controlling the band gap of 2D materials or changing the material into an artificial membrane. This is an emerging application that this process can facilitate quite well. Of course, we don't stop there. We then start modifying the thermal resist itself as well by, for example, infiltrating it with a metal oxide using atomic layer deposition. So this was work done in collaboration with IBM and imec, where the PPA itself was turned into aluminum oxide using a few cycles of atomic layer deposition with very long cycle times. You can see the details of what was done in the publication from 2018 here. Using this method, very high aspect ratio pillars were achieved. This is also something that can be expanded to arbitrary shapes as well. Another way in which the PPA can be modified is by hanging different groups on the polymer itself. So in this case, we have worked with all-resist in order to hang tetramethyl, let me see, yeah, TMS, tetramethylsilane groups on the PPA. And this has increased the selectivity when we are etching quite a bit. So the etch resistance of the PPA that has been modified with TMS was a factor of 2 to 3 higher than the pure PPA. And this allows us to make even thinner films of PPA and therefore even higher resolutions. Right? So I would like to just emphasize here that the high resolution features that we can pattern with the NanoFrazor can, with these processes that we have presented, be transferred into the underlying substrate, and also that these ultra-thin layers are very useful when used carefully. They can also be applied very repeatably. We keep working with PyBond and all-resist and IBM and lots of very exciting partners to keep developing these materials and making them then commercially available in research quantities as well as large quantities for our users. Do get in touch with us if you would like to know more about them over our support, as well as looking up the details in our recipe book that is available as of today.